tear it up.
Already did.
Already did. Good, you're ahead of the game. Here is the new and improved and accurate calendar. I realized what I did messing up the calendar. I have one posted, but it's the 2016 April. I'm whatever. So here is new and improved.
That's a little late.
Which are you?
The CLU.
Oh, cool.
Section's part of.
But they haven't heard back. When was the deadline for applications? Was it long ago?
I don't know how long.
I may see her later today. I'll ask her. Kenzie? Kenzie?
Kenji, maybe?
Kenji? Greg?
That's her.
Renzo? Jessica? Anthony? David? Pardon? That's okay. Sean? Tyler? Times 40, 120 students, and it's hopeless. With a class this size, I'm going to learn your names. There are colleagues of mine who would know your names by day 3. I'm not. I'm really great with faces. That's visual. I'm really terrible with names because there's no logic to any of your names. I mean, that was one of the appeals to me of mathematics. I know some of you have survived in mathematics by memorizing things. I survived in mathematics because I have a terrible memory, but if I forgot something, I could logically fill it in with stuff I knew. In French, if you forget the gender of table, there's no hope. In biology, if you forget the name of some muscle, there's no logic. It's named after somebody who first discovered it, or a bone. I said it in an anatomy and physiology class. It was overwhelming, the vocabulary. Math is gentle. So, I think one of the things I'm going to try is to have a little nameplate that sits in front of you each day for a while. We'll start that. This is my goal. You're going to have to bear with me. I would have been terrible as an actor trying to memorize script or something. On the other hand, a math class, a math lecture is easy. You just start with the problem, and then there's step 1, and then there's step 2, and finally you're at the end. That's cool. So anyway, okay, you each have the new calendar. If you came in late, there's the new calendar. A few of you have not yet turned in the survey. Please do so, and then I'll report the composition of the class, who we are. And the first thing is the errata report. That's a fancy word for errors. These are now fixed on the web. There's an errata in the errata. Yes. So those answers are now fixed. Greg,
Yes.
$1, 2, $3.
What?
He reported the 3 errors.
Sweet.
I pay for errors.
Thank you.
Well, you're not, I hope you don't get rich. The point is, I'm really serious about finding these things and fixing them. So if you find it, please send me an email, describing what's wrong. The very first thing you should do is check on the web to see if perhaps somebody else has already reported it and it has been fixed. But typically, he reported it, early afternoon, and by early evening, it was fixed on the web. That's the way things get fixed. If I was at a university, I would hire some graduate students to work all the problems and check the answers. In the case of one person I knew, his son was approaching that age, so the father employed the son all summer to work calculus problems.
That's good practice.
Pardon?
That's good practice.
Good practice, yeah. Son was getting ready to go off to university. Anyway, yeah, the worksheets are a way for me to give you feedback early on. For example, in problem 4, the volume of the whole, several of you gave me the right answer as a number, but if a problem has units involved, your answer really ought to have units involved. So, the first 3 did not have any units, so that's fine, you just needed a number. But just a reminder of those things. Again, I'm going very quickly over 14.0, 14.1, because my assumption is that this is review and that you simply need a little bit of reminder. So the problem number 14.1 is we have some kind of a rectangular domain down in the XY plane. Let me call that R for region. And above that, we have some kind of a surface. So this is, Z is a function of the X and Y in the domain. And our goal is to figure out, at least to start with, what is the volume between that surface and the XY plane? Well, back in Calc 1, it was easy. You simply split things up over each little delta X region. You found a height. That's f of delta X. And then you add. So what's the area of this rectangle? X. And that gave you the area of 1. What did you do then?
Add up all.
Add up all of them. So what you got was the area was approximately this, and you muttered the magic words, Riemann sum, and you took a limit as the little delta x's got small. And we ended up magically with a nice integral from a to b of f of x dx. The same kind of thing is going to happen here. If we've got, let me think of, if we're going here from C to D, let me think of partitioning along the y-axis. So this is location y, and this has thickness delta y, and what I end up with is one slice like that. So I just happen to have a model. That's what that's for, yeah. Oh, look, okay. So, if I make these slices, another image is you've got a solid loaf of bread, you're going to make slices here, parallel to the x-axis, and then we'll have a bunch of slices. What's the volume of this i-th slice? Area times the thickness.
Delta y.
So I'm going to need a face area. The face would be one of these little pieces here. So if I think of the face as being this front piece, that's in square inches, and then times what?
Thickness.
Times the
Delta
thickness.
x.
Okay. That's going to be approximately the volume of that. Well, the thickness is pretty easy. The thickness is simply our delta y. Oh. We know how to find an area. That's simply an integral from a to b in x. That's the integral of f of xy times dx. So, for this first slice, I integrate and I get this area times the thickness. For the next slice, I integrate and get this area times the thickness. And then mathematic, etc., dot, dot, dot. I keep it up. So how would I get the total volume? What would I do with all these?
Add them up.
Add them up. Oh, look. And we happen to have another Riemann sum. So if I take the limit, there's a difference between the area of the front face and the area of the back face. But if the slice was incredibly thin, for example, there's really no difference between the front area and the back area because this is so thin. So what we'll do is we'll take the limit as delta y approaches 0, and we end up with the integral dy of the integral dx of f of xy. And what is, let's see, x was going from a to b. And what about y? Well, whatever the endpoints were. So, as we get into new stuff, I'm very often going to drag it back to things that I hope are familiar to you. I mean, what we did in, what that was Calculus 2, the same ideas work here. I could have chopped things up. I could have partitioned here with the delta x, and partitioned this way with the delta y. And what would be that area then? That's often called dA. How much is the area of that then? That's delta A would be delta x times delta y. So very often you would see this written simply as a double integral of the function with a dA and an r down here. What that's saying is we want the double integral over that region with respect to the area, but we don't care whether it's dx dy in that order or if it's the other order, dy dx. So, the good news is these are really easy. So for example, if we had the integral, oh, let's keep life really easy. 18x squared y squared plus 6x. It's just like algebra in the sense that you're always going to work from the inside out. And even though I haven't labeled it working from the inside out, the dx, the inside dx goes with the inside integral, so x is going from 0 to 2. And now we do, I'm ignoring the red integrals. What's an antiderivative 18x squared y squared with respect to x? This is, you spend a lot of time taking partial derivatives. This is sort of a partial antiderivative. Yeah.
6x cubed y squared. Is,
6x cubed plus y times
y
y
cubed.
squared, sorry, plus,
5 over 2x squared.
that's a 6.
Oh, 6.
I wanted to make my life
Three.
easy.
So
So what is
3x squared?
3x squared. And you can do a super quick mental check, take the derivative of that with respect to x. Hey, it worked. You were starting to say plus.
Oh, and then I was going to say dy. Well, I guess plus.
Let me write it there super small, because now tell me about x. X from where to where?
0 to 2.
0 to 2.
X equals 0 to 2. Putting in the 2, I have 6 times 8 y squared plus 3 times 4 plus k
Minus k.
minus, when
K.
x is 0, what do
K.
I have?
K.
K. So in taking an antiderivative, yes, we always get a family of answers. In doing these things, I never bother writing down the k because I know that's always going to happen. So what I'm left with here is 48 y squared plus 12 But that was just the inside. So what's our antiderivative here?
16y cubed,
16y cubed
12y, plus 12y.
equals 12y, evaluated from y equals 0 to 3. 16 times 27 plus 12 times 3 is some number. One of you will tell me I'm pressing buttons.
468.
468, thank you. What that represents, since this function is always positive, in fact, it's this kind of a picture. We really have the volume. What if the function was sometimes positive and sometimes negative? What would be going on? What happens with integrals? If that turns out to be a 9 area and that's a 4 area, then the integral from a to b would be what? 5. So it's an integral. If way back in calculus, if you thought of an integral as assigned as an area, that's fine. But then you need to adjust your thinking a little bit to say an integral is a signed area. Area could never be negative, but an integral could be negative. Similarly here, if our function f of xy was always positive, we would for sure have a volume. If f of xy was sometimes positive, sometimes negative, we might have this situation where there's an interaction and the double integral just gives the sum of the positive plus the negative. What about the integral from 0 to 2 of the integral from 0 to 3? Anybody care to make a wild prediction?
It's the same.
It's the same. You're confident that it's the same.
Yes.
Would you care to wager?
Is it based on Fubini's law or something?
Yes. There is a theorem called Fubini's theorem that guarantees it. If you don't want to get so fancy, again, think of the slice of bread. The volume of the loaf doesn't change if I cut it this way versus if I cut it this way. And that's all that's happening by changing the order of integration. Yes. Say it with confidence. Yes. Really? Are you sure? We can do this quickly. What's the antiderivative with respect to y?
X squared y cubed over 3. 6xy.
6xy. Y from 0 to 3. 6x squared times 27 plus 6x times 3. Minus 0. Whatever 6 times 27 is. X squared plus 18x. Now we have to integrate x from 0 to 2. No problem. 2 times 27 cubed plus 9x squared Did I do it right or wrong? I did it wrong. We're going to 2. There we go. I sure hope that gives the same result. Okay. The key, again, this is review in the next section. I'll slow down a bit. But basically, where did these double integrals come from on a rectangular domain? It came from slicing. Approximating the volume of each slice, adding them together, taking the Riemann sum. So that's the how, that's the where it came from. The how is, simply work from the inside out. In 14.2, we will have non-rectangular domains, and life is going to get more interesting. And interesting in the sense, we'll slow down there, but rectangular domains are no challenge, except for finding antiderivative. Okay, just fine. What would be an antiderivative of e to the xy? Oh, I'll start you off easy. How about the antiderivative? 3x plus 2y with respect to x. Well, you're expecting to start with e to the 3x plus 2y. But if you take that derivative, you get e to the 3x plus 2y
Times 1/3.
With respect to x, you get times 3. Therefore, how do you need to adjust it? As he said, 1/3
Plus K.
plus k. On the other hand, y what do we need here?
Half.
A half. So what if we started with the problem I was originally thinking of?
One over y.
E to the xy, for sure. If we're taking the partial with respect to x, would be e to the xy times
One over
y.
y.
So we need 1 over. I mean, this is one of the reasons you would be doing homework problems, just to get a little bit of practice with this. How many should you do? As many as you need. Make sure you ask. So, whoops. Show me what you know. Oh no, it's making us work again. The point